Now we will go through the implementation of the OCP to AXA conversion part. So as you know, when the masters are requesting a read to the OCP client, it will return with the corresponding data. So these data has to be returned to the appropriate masters. These read returns are identified by using the tag information. So as you know, we have two masters, and out of the 16 tags possible with the 4-bit wide tag in every interface, the first 8 tags are assigned to master 1, and the second 8 tags are assigned to master 2. In other words, all the interface tags in the master 1 interfaces will be between value 0 to 7, and the tags used by the second AXI master will be between 8 to 15. Thus, whenever OCP is returning a tag information, returning a read data based on the tag, if the tag is anything between 0 to 7, it will be returned to the AXI master 1. Otherwise, if the tag is between 8 to 16, then that read return data should be returned to the AXI client 2 or AXI master 2. Now in the OCP to AXI path, we have 3 different submodules, which are OCP read return frontend, OCP to AXI converter 1 and 2. So in the OCP read return frontend, we will accumulate all the 16 data which are coming in different 16 clocks into a single packet, and we will send it to these two modules, or we will route that packet to any of these modules based on the tag. And once we have a complete packet available in an OCP to AXI converter, it will send in its appropriate interface or the read return interface one by one. Now we will go through the implementation of OCP read return frontend. So in the OCP read return frontend part, the OCP read return data coming through the OCP interface will be accumulated up to 16 data and sent as a single packet to the output, and thus we are using 16 flip-flops within this module. And whenever we have a complete packet available, that is whenever the last signal in the OCP interface is asserted, that point we are indicating there's a valid complete packet available into the output of this module, and the upper module will process it. Now we will go through the coding part. So this is a module OCP read return frontend. It is having an input clock and reset, and an OCP interface is passed to this, and again there is an input hold which is used to hold the OCP interface if needed, and output are a complete OCP read response packet and its filed information. So these are the internal signals used. And next, the OCP interface.m response accept is equal to not hold in. Thus the input hold in is used to hold the OCP interface if needed. If this particular DUT is not able to process further packets, it can assert a hold in to this module so that it will be sent to the m response accept the signal in the OCP. Next, we will decode the last packet in the OCP interface in a signal rlast. So if whenever you have valid response available and the S response last in the OCP interface is asserted, this will be set to 1, otherwise it's 0. Next, the data in the OCP interface is set to a D in signal for easiness, and again we are saying a D count, which is used to count the number of data in this particular packet so that it can be sent as a length field in the output packet. So D count next is equal to, if when it is R last, it is reset to 0. Otherwise, when we have a valid data available and response accepted, that point the D count next is equal to the current value plus 1. Otherwise, it's equal to the present value. And again, declare is used to clear the flops, and whenever we have D count 0, that is the point where we should clear all the flops, and since it has negative reset, the whole condition is negated. Now these are the flopped versions of the D count, the last and the D count previous and the ID previous. And in the output packet, you can see that the output valid is equal to whenever we are detecting a previous last condition. So we are asserting a valid condition, a valid signal to the output whenever we have completed receiving a whole packet in the OCP interface. That is, whenever we had received the last information previously in the OCP interface. Now packet valid is equal to R last previous, and at that point when the packet is valid, the OCP read response packet.id is equal to the ID previous if it is last condition, otherwise it's X, and again the length is equal to d count previous, and that 15 data values are assigned with the 15 flops used. So you can see that d15 to d14, d13, all these are the output of the flops. So these flops will be flopping out the data input at a point when the d count is equal to the particular value. Same, when the d count is equal to 0, d0 will be flopping the d in. When the d count is 1, the d1 flop will be flopping the input data. You can see that the d in is the input data in the OCP interface. It is a slave data. So these flops will flop the incoming data in the OCP interface one by one whenever the D count is incrementing, and the decrement is incrementing at a point whenever we till we are getting the last W last, the R last signal in the OCP interface. Thus we are flopping out all the maximum 15 datas and forming a complete OCP packet or OCP read return packet with maximum of 16 datas and ID and length. So ID, length and 16 maximum 16 datas are sent as the output of this particular module, and they are again combined to a single packet called OCP read response packet. Again you can see that the type of this packet is AXI data packet. So this we had defined in the previous AXI write front end file. So AXI data packet is nothing but a packet which is having ID, length and 16 datas. Thus this module OCP read return front end will wait for all the data to be come in the OCP interface in the response channel, response path, and it will be sending us a violet packet to the output.